So I'm here to talk about data plane signaling. So first of all, I don't know, not everyone might be familiar of what it is. It is basically it's supposed to define the interoperability between control planes and data planes. So some key aspects or some facts here. Its goal is to make independent the control plane from the data plane and to define the protocol for those two to communicate. In doing so, it defines some state transitions. It defines push and pull scenarios, what those are. It also defines finite and non-finite transfers. It defines the possibility for back channels. And there is, of course, the need for bilateral registration. So every control plane needs to know their data plane and the other way around, because there is always a reply, or it's a two-way communication essentially. So these are the key aspects what DPS defines today. Again, as a bit of a picture to know what I'm talking about. So when the control plane receives instructions via data plane, via the DSP, I'm getting confused with the acronyms. The data plane needs to be informed, like a transfer is started, a transfer is paused, or a transfer is errored out because some policy isn't fulfilled anymore. Then there needs to be communication between those two. So control plane, data plane, that communication, the one in the diagram that defines the flow of data. Then the second arrow would be the reporting back of the data plane to the control plane, which informs the control plane of state transitions. For example, if a data transfer has finished or has run into a problem, then the data plane needs to report that back to the control plane so that the control plane then can report back to the counterparty. And finally, the third aspect of the protocol is the registration. So of course, like I said, the control plane needs to know their data plane as well as the data plane needs to know their control plane. This does not specify whether the control plane and data plane is a one-to-one matching. So you could have one control plane and 53 data planes if that's what your deployment looks like, but still they need to be registered. So earlier I hinted at the differences between push and pull. So a push data transfer means that the provider initiates the actual transmitting of bits and bytes and pushes it into the consumer's data endpoint. This could be HTTP. So the easiest way to think about this is the consumer exposes an HTTP endpoint and the provider then performs a post request into that endpoint. That would be the provider pushing the data. Conversely, for us developers, it's more intuitive that way. The pull scenario where the provider exposes an HTTP endpoint or some other protocol endpoint, and the consumer performs a pulling request. In REST, that would be a GET request. Of course, there is other protocols that you could implement, like could binary transfer, whatever you want. But these are the two general directions in which we transmit data. Then there is, as a bit of another dimension to this, there is the differentiation between finite and non-finite data. So just imagine transferring a file via I don't know, SFTP or something. It starts, then it transmits, then it's finished. The file is done, basically. So in contrast to this, there could be an event stream like Kafka or some other event pipeline where the stream basically is open and the data transmission is non-finite because you never know whether something else is in the pipeline. Or remember, I don't know, or just, sorry, imagine some open-ended API where you can, pull status information about some system. That API never terminates unless the system goes down. So then DPS also specifies specifies back channels. And what we mean by back channels is some, I don't know, quality reporting. It could be a reply or an acknowledgement. So say you pull status information about a system, and then through the back channel, you want to supply feedback, like whether that's understood or whether the status is good or the data is acceptable or some back channel that you might have. Or clear to send next package or clear to receive next package, something like that. That's a back channel. It does not have anything to do with the actual data transmission, but the key aspect to remember is that back channels are always provider supplied. So as per the protocol, it's always the provider who exposes the back channel endpoint. Again, it doesn't matter whether it's HTTP or some other protocol. It's just a generic description. Let's just browse through this really quick because I'm imagining that it's probably better for you if you read this in detail in the specification, but the data flow state machine is as follows. There is a couple of states here. There is the preparing and prepared, which means both sides set up some sort of data transmission. So for example, the provider could, if it's a pull transfer, I don't know, set up encryption or expose the endpoint, spin up some streaming service, whatever that is. Or if it's a push scenario, the consumer could do the same thing. Then there is starting, means both parties are ready to send or to receive. Started then is basically the state where the actual transmission can happen. Then we have suspended. This could be due to a temporary outage. The consumer doesn't want to pull data for some time, so it might choose to suspend the data transfer. No data moves. And then the data transfer, if it's a finite one, it completes, which means that's the normal termination. And then it could be terminated, which would be an error of some sorts. There is a question, I believe, Christoph?
Yeah, just a short question.
Yeah.
How do you decide whether you go the prepare branch or directly start the control plane? Can you have a sentence on that maybe?
Yes, you always go through the prepare state. It might be a no-op. So if you don't need to prepare anything, you don't prepare anything, you directly advance to starting.
Oh, so that depends on your local configuration, kind of.
Yes.
Okay, thanks. Okay, yeah.
Or in your implementation of your data plane, you might even choose not to go through preparing, to always go to starting.
Okay. Yeah, so that's really implementation dependent. Okay, thanks.
Cool. Okay, so then we have the data address, and two of you who have got their hands dirty in the EDC code base already or in some other specifications, data address pops up here and there. It is basically a data object that tells you where the wire protocol endpoint is and what properties you need for it. Meaning, does it need authorization or does it not need authorization? So as it says, in the pull scenario, this means the data provider exposes the endpoint. Then the provider also needs to tell the consumer about the authorization profile. So in plain terms, this would be, I'm going to give you data here, and that's the credentials that you need to access it. Conversely, if it's a push scenario, it's the consumer that says, please put the data there, and those are the credentials that you need to authenticate. So this is transmitted as part of the communication. It goes through the data plane signaling as well. It goes to DSP because, of course, that needs to happen. And then, of course, if the endpoint doesn't need authorization, then there is no endpoint properties with those objects set. Now, I've talked a bit very briefly about the specification and what it is. I also want to say one or two words about the current state of code that we have for this. So there is a bit of code already. There is SDKs that you could use that implement data plane signaling. Most notably, there is a Rust package and there is a Java package. All of those are situated in the Eclipse Data Plane core repository, or project, sorry. So these two are basically SDKs. You can include them in your code base, and you have a DPS compliant code. Those include state machines like the signaling endpoints, callbacks, error handling, some other things. There is also a Go and a .NET package, but these are not up to date. They are on our to-do list to bring them up to date, but that hasn't happened yet. So our first-class citizens at the moment are really Rust and Java. Why Rust and Java? Java because another big project that we're working on, and that's also relevant for EDWG, is the EDC connector project and with all its associated components, and that is in Java, so that's an obvious, almost a foregone conclusion. And Rust, because it's very, very efficient, it's small, it's secure, and we imagined that for a lot of data plane implementations, efficiency and performance will be interesting. And also that's why we created what we call the Siglet. That's basically almost a data plane implemented in Rust. It has distributed locking and all those good things that are written here, token exchange, token renewal, everything. And what you can do with it, you can use it as a sidecar container in your application. It exposes a small API. Basically your application talks to Siglet, and Siglet handles all of the data plane signaling tasks, including token refresh, everything. Right. So as a bit of a TLDR, data plane signaling is a REST-based protocol. No JSON-LD fanciness here. It controls the data flow lifecycle and the data flow or the lifecycle of a data flow, so to speak. You can use either Siglet as a sidecar for maximum comfort and with the least contact with data plane signaling, or you could use any of the SDKs. Naturally, if you want to use a very, a non-mainstream programming language like, I don't know, Haskell or assembly, you could write your own SDK as well. The specification is at the first link and the code is at the second link. And that's about it. Any questions?
Thank you.